I'm Shannon Stannis. I work for the Wabash River Enhancement Corporation as the Watershed Coordinator for the region of the Great Bend of the Wabash River. This soil health video is put together intentionally for those that own agricultural land but don't farm it themselves and want to learn more about their farming operations. The information in this video is relevant to everyone as the health of our agricultural soils have community impacts on and off the farm. The health of our soils is impacted by how it's treated. In this video, our guest speakers are going to teach you how you can assess the health of your soils through a simple walk through your farm, looking at 4 important topics: your soil cover, residue breakdown, soil crusting, and the water stability of the aggregates.
Hi, my name is Stephanie McLean. I'm the State Soil Health Specialist for the Natural Resources Conservation Service here in Indiana.
I'm Joe Rourke, and I'm the agronomist for the Conservation Cropping Systems Initiative. I work with Stephanie quite a bit, and we work all around the state with farmers and landowners, just like you guys, on issues around soil health and how to improve your land. So what we want to start off by showing you is this demonstration right here. We have a pair of soils, and these are both the same soil type. These are actually Miami soils. These are good silt loam soils, representative of a good portion of what we have around the state. And the only difference between the two is the management of those soils, how they're farmed. So to start off with, you can see that this one on your left is quite a bit darker, right? You maybe can see some of these little pores in here, some evidence that maybe there was an earthworm or some sort of little soil critter that lives in there. You can see some roots intact. You can see some other evidence of life in this soil.
So the soil that I have, like Joe said, it's the same soil type, but as you turn it around and you look at this soil, the things that Joe talked about, earthworm channels, root pores and things like that, you don't see very many of those things in this soil. It looks a lot more compacted together, pressed, no pore spaces, and no topography within this chunk of soil. It's just very hard feeling and not a lot of pore spaces in there. And if you put it right next to each other, other physical properties that you notice that are different is definitely the color. We see a significant color difference on these two soils as well.
Let's talk a little bit about the management of these soils. This soil in my hand is from a good long-term no-till system that also incorporates cover crops over winter and when there isn't a crop in the field. The soil that Stephanie's holding, the same soil type, is from a heavy tillage system without cover crops. So now we'll drop these two soils in the water and we'll take a look at how they function when they get wet. So right away, what we're seeing, what's happening here is water is rushing into this soil, and here where we have those connected pore spaces in this healthy soil, or this soil from this healthy system, you can see air bubbles coming out the top, right? So the water is rushing in and the air is able to make its way out.
On the other side here, this soil that we had talked about that didn't have a lot of those pore spaces and root channels, that water is pushing on that chunk of soil, and that water is trying to get in, but it can't. And so as that pressure keeps building up, that soil starts to fall apart. And all of those individual particles of sand, silt, and clay are sloughing off of that chunk of soil and coming loose in that water column. So as you can see, that's falling apart here right before your very eyes.
So as it continues here, you can see that this soil is still able to hold together. These soil particles are actually held together by biological glues, as well as those fine root hairs. So by not tilling this soil, it's able to hold itself intact when we don't go through and break it up with a tillage implement.
On the other hand here, because of all the intensive tillage in this system, any of the biological glues that are maybe built up during the growing season from the bacteria and the fungi that live in that soil, that stirring and that tillage destroys that every fall and every spring. So those biological glues are decomposed and break down, and then that soil isn't able to hold itself together. So this soil over here The one that holds up under the pressures of water and stays and has aggregate stability, this is our healthy soil. So we call this healthy because it has function. Like Joe had mentioned earlier, it's able to infiltrate water, it's able to hold up to those pressures. And so this is what we consider a healthy soil because it has function. And this soil, or lack thereof in this instance here, this soil is what we would consider to be unhealthy because it doesn't have those functions that we expect a soil to have. The ability to withstand the pressures of water, the ability to infiltrate water and then release water to later when it doesn't need it, or back to the plant when the plant needs it. So this would be considered an unhealthy soil because it can't stand up to the pressures of water. All right, so while we're here today, we're going to look at a few things in the field that will hopefully help you when you go out and look at your field. The first things that we're going to look at soil cover, we're going to look at residue breakdown, we're going to look at surface crusting, and then we're also going to look at water stable aggregates. So those are the 4 very simple things that you can do just walking out into your field and looking at that soil surface and doing a few simple things right there.
So this soil is managed without tillage. These plots are just no-till here. So as we look down at the soil, you can see the beans are pretty far along here, these soybeans, and they've dropped their leaves and some of the branches onto the soil surface. So it looks like we have pretty good cover here. It's very important to remember though that these soybean leaves are going to degrade very fast. Right? These will be here 30, maybe 60 days, and those will be gone. So for a healthy system, it's important to have soil covered for as long throughout the year as you can. Here where we just have no-till, without the addition of cover crops, our soil cover is only coming from the crops that we plant. So in season, it's the growing crop, but then over winter, after harvest and before planting of the next year, it's that residue from the previous crop that's providing the bulk of our soil cover.
So if we want to think about a soil being a healthy soil, we would look at that soil and we'd want to see continuous soil cover on there. And when we say continuous cover, I'm not talking about, you know, feet and feet and feet of soil cover or mulch on that surface, but a nice continuous amount of soil cover protecting that soil surface. When you look at this, think about how it's distributed across the field. As the combine's coming through, is it evenly distributed, or is there big piles of residue in certain places, and is that cover uneven across that soil surface?
So once you're done looking at soil cover, and while you're still considering soil cover, it's also important to consider residue breakdown. Because there's nutrients tied up in these residues, and because we don't want to see these residues piling up and blocking the field, we want to see evidence of these residues breaking down.
And when we talk about residue breakdown, the most important thing that we really want to emphasize here is the biological breakdown of residues. So the shredding and tearing apart of residues by the macro and microfauna that live on our soil surface. So this isn't necessarily the sizing of residue because of tillage, because again, that is the artificial process there that occurs, or that some people do. we really want to look at that biological aspect of it, because that gives us an indicator of how biologically active your soil is and if we have nutrient cycling. So yeah, and biologically active soil, so when we have more micro and macro fauna in there, tearing those residues down and sizing it out and decomposing those residues, when we have more cycling like that, we will have a healthier soil. So the more of those saprophytic fungi and decomposing organisms that you have, the faster that these residues will break down. And they're the first ones that come in and start to simplify these carbons so that other bacteria and other fungi can come in and then feed off of those residues as they become more and more closer to, say, a simple carbon. So if you look at the corn stalk that I have right here, as I break it open, this pith that's in here, that white pithy center, is not very decomposed at all. It's still pretty clean residue and it's still pretty intact. And this corn stalk is a year old right now. And so ideally we would like to see this more decomposed than it is. Even if you look at the outside of the stalk, it's still actually quite yellow. And so that just is an indicator that this hasn't decomposed as much as we would like to see it.
So I found a piece of corn residue here, and if you crack it open, you can see here at the node of this corn stalk that you've got some evidence of breakdown here. On this end, that inner pith is still a little white and not showing a lot of signs of breakdown, but you can see some of the strings here, and it's not perfectly intact. And here at this end, of course, you can see it's darker and it's falling apart more. And then here farther up the stalk, you can see that there's not much left to that corn stalk. We often talk about residue that we don't want it to see its third birthday. So while soil cover is important, we want evidence that that residue is cycling, right? That residue is breaking down slow enough that it still provides some soil cover, but still fast enough that it doesn't pile up. So we're looking at that sort of 1 to 2 year range that we want to see residues breaking down in. And you can do that by just seeing if the residue that's there is showing signs of breaking down, as well as can you see evidence of more than 1 season's worth of residue there, or 2 seasons worth of residue there. You'll notice while there is some corn residue here, there isn't a lot of corn residue like there is in a brand new harvested cornfield. So you can see different sizes of pieces of corn residue. And if you look at, if you can find where a row was and you pull a stalk out of the ground, does it pull out easily? Or is it hard to pull out, like the roots are still connected and haven't broken down yet?
So for comparison, I just pulled a corn stalk out of the cornfield right next door here, and this would be what would be that first year's corn stalk, or just finished corn stalk for the year. So again, pay attention to how yellow, how full of color still the outside of this stalk is, and then the pith itself and how intact it is. And so that idea is that we'd like to see, a third to a half of that gone within a year. So if you look at what Joe's got here, 1 year later, we're seeing a significant amount of that interior of that corn stalk actually start to be decomposed. If you come back to a corn crop again, so you've gone through your corn, planted and harvested your soybeans, you plant corn there again the next, that third year, and you have corn stalks that are still of having this color, this yellow tint on it, and they're not faded out and grayed out, you really start to want to ask yourself about that residue breakdown. And are we having a lack of biological activity in that soil so that those residues aren't able to cycle? Because again, nutrient cycling is one of the most important things that we get from having a biologically active soil and residue breakdown. And so we want to start looking at this more critically so that we can understand if we have nutrient cycling or not.
Corn cobs are often one of the slowest things to fully break down. So if you're in a corn and soybean rotation, or if there's corn in the rotation, corn cobs are a good thing to look at for residue breakdown. So on your right, you can see a corn cob that's a year old and it's been out here on the soil surface. And you can clearly see when you compare that to this new ear of corn, the difference is there. So this pith, when it's new, is nice and white and firm. And here there is no pith left. And that's one of the fastest things to break down in a corn cob. You can also see the differences in the color, right? It starts this sort of red-orange color and will end up brown. On this particular example, you can see this white here. That's likely a saprophytic fungi. That's one of our main residue decomposers.
So the next thing that we talk about when we are looking at the surface of your soil is surface crusting. And so when we think about surface crusting, typically this isn't a situation where we would see a lot of surface crusting because we have good soil cover. And where we would see soil crusting is when that soil is overworked and then left bare for raindrop impact. But let's take a look at this soil surface and talk about what crusting is or why we're not seeing crusting here. So as I brush this soil cover away and these residues, you can kind of look at this soil surface, right? And as we look at it, it tends to break apart really easily, and we tend to have aggregates here at the surface, and so that soil isn't crusted at all because of all of that surface cover and all of that protection. And as you brush more and more of that soil away, you can again start to see that texture or those soil particles and this almost what I would like to call topography on that soil surface on these soils that are not crusted. Our crusted surfaces will typically be really smooth over the surface because those particles of sand, silt, and clay and those aggregates that we're talking about here, when we have crusting, these aggregates will start to melt away and then collapse upon each other. And then when that soil is dry, we're left with that surface that's crusted. So in this situation, because of the good soil cover and again because of the no-till system, we aren't seeing much surface crusts. And so this tends to be more of a healthier system that we have here because of that good soil cover and that lack of a soil crust. When we have good soil cover, good residue breakdown, and no soil crust, we see better function that occurs in these systems. So when we think about a soil crust, we might see that in places in your field where the residue doesn't stay. If the end rows tend to lose more of their residue or more traffic is over that area, you might see more crusting in those parts of the field. So what you want to do is you want to look for that crust or understand if you have a soil crust or a surface crust. Does it cover that entire field? Is it a large portion of that field or is it just small areas? And try to understand how much of an issue you're dealing with in that type of scenario. When you do have a soil crust, the biggest thing you want to think about is the fact that that water is not able to infiltrate. So the question you want to ask is, are you okay with 50% of your field or 60 or 70 or 80% of your field not being able to infiltrate a rainfall event? So the goal is to have as little of a surface crust as possible on your field.
So our last indicator we want to talk to you about here is going to be water-stable aggregates. But in order to do that, I want to be able to show you a comparison between this no-till soil and a heavy tillage soil. So let's get some of this soil to take with us over to our next plot. We've moved fields, and we're going to take a look at some of our in-field assessments to look for some of our soil function again. So just like we did over in the no-till, now we've moved over to a full width tillage system. So in the fall, this gets a tillage pass, the residue gets incorporated, and this soil will lay bare all winter long. after harvest. In the spring, they'll come in and they'll do another pass.
So if we want to talk about soil cover here, this is where we would take some time to, again, walk out into this field and look at that soil cover. And there are some differences that you notice here right away. What I notice is that there's a lot less cover in general. So we see a lot more bare spots in the field, and that soil cover isn't really spread evenly throughout the soil surface or over the soil surface. So again, taking some time to look at this soil cover, seeing how much is out here, and then seeing how evenly it is distributed across the field. Because again, that soil cover, if you remember, it protects that soil surface from raindrop impact. It protects that soil surface from the solarizing effects of the sun, and it also helps regulate soil temperature and soil evaporation or moisture evaporation from the soil surface.
So when we think about residue breakdown, while we do want to see evidence that the residue is breaking down, it's important to remember that there are nutrients tied up in those residues. So if we do our fall tillage pass and incorporate those residues into the soil and they break down quickly, those nutrients that are in that residue are released during the winter time when there isn't a living root out in this soil to help hold those nutrients in the field. In addition, because there's no soil cover, this soil has a tendency to crust over. So if we look for evidence of crusting, because we can see so much bare soil, we know that we're likely to see evidence of crusting.
Again, the idea of what happens or how a soil crusts is we talk about soil being overworked. So when that soil is constantly getting stirred or tilled and constantly, again, getting overworked, those biological glues that we had talked about earlier that help hold those soil aggregates together, those glues are broken down, and then those soil particles are just loose soil particles of sand, silt, and clay. And then that soil gets rained on, and then those soil particles collapse upon themselves, and that's what causes a soil crust. So again, overworked soil, no soil cover, no residues on this system leads to a really high chance that we're going to have a crusted soil. Unfortunately, when we have soils that are crusted, the most common response, or historically the most typical response that we've seen, is that farmers want to till that soil to break up the crust, which in turn continues to overwork that soil and resulting in more crusting occurring after that tillage pass is done.
If you remember, our fourth indicator is water stable aggregates. So just like we did with the no-till, we want to take some soil back with us to be able to show you a test that you can do at home. We're going to show you a test called a slump test that you guys can do right at home pretty easily on your own land. So you saw us take the soils with the shovels right from each different management system. So Stephanie has the soil here from the no-till behind us. And here in front of me is the soil that we took over from the full width tillage. You'll notice we pulled that soil, and just like we've been talking about, we want that soil from that top couple inches, right? We want our most valuable topsoil because it's your most valuable topsoil that you really want to protect and keep on your land. And with soil health, that's where we're talking about all of our function being and our most important functions being. So I'll grab a piece of this crust and Stephanie will grab a piece of that surface of that no-till soil. And you just want to crumble it up how it wants to crumble. You don't want to mash it, right?
Yeah, you want to break it up into its fine natural aggregates that we're having here. As I'm pulling this off the surface of that no-till field, again, like Joe said, we're trying to get it right from the surface. I like to get it within the top inch or two of the surface, and then I just want to start letting it crumble on its own. And if you can kind of notice, what as Joe and I are breaking these up, they break up differently. And as we're crumbling them in here, like you said, don't mash it. We also don't want to necessarily overfill this or pack it down. We just are looking to naturally fill this in here. If I get any big chunks of residue, I'll pull them out. And again, the reason why we're looking at the surface is because of that interface, that soil and air interface. If we can't find water-stable aggregates at the soil surface, it doesn't matter if we have water-stable aggregates 6 inches down or 12 inches down, because it's right at that surface where we want to look at that water-stable aggregate.
So then we just have cups of plain tap water here, and we're going to take the sieves and just sit them in the tap water and watch what happens. So if you get down and look, even though it's not meant to act like that slake demonstration we showed you in the beginning, the tubes, it is functioning a little like that here. So you're seeing, immediately you're seeing this unhealthy soil break down into its individual particles, its individual sand, silt, and clay particles, and watching that soil cloud, or that water rather, cloud up. And here in the no-till soil, we are getting a little bit of that, we are getting a little bit of material through that fine mesh screen, but we're not seeing it cloud the water up like we are here in the tillage system, the unhealthy system. So that's an indication that even though we're seeing some soil material fall through, those are probably micro aggregates. So those soil particles are still glued together, even just in very small pieces, and they're falling to the bottom rather than clouding up the water like we're seeing here.
We wait for about a minute, and then at that point in time we take them out, the strainer out of the water, and we're going to dump them onto our shovel right here. So we're going to pick this up and we're going to let that free water kind of run out of it a little bit. And then we're going to take it and we're going to dump it on our shovel. So right away we can see some big differences in aggregates. The soil that I have here, just as a reminder, this comes from the no-till system. So again, it's no-till only for management. We don't have any additional cover crops or anything else, but you can still see aggregates, those shapes and those irregular shaped soil particles and aggregates throughout this massive slump pile here. In comparison to Joe's soil,
over here where we've had heavy tillage, where we don't have that soil covered, where we have residue breakdown that's much too fast because of the mechanical incorporation, and because we have that crusting, right, those aggregates are not protected, they're exposed all year long, and they just break down. Opposed to where we do have soil cover from the no-till, and we have a slower residue breakdown throughout the year, those aggregates are more protected, and you can see the difference here.
Those aggregates here have completely melted away. They're not existent anymore. We've kind of left with a shiny sheen at the surface. It's really smooth, and you can't tell that there was any chunks of soil in there. It looks like a massive pile. Whereas here you can still see those, still somewhat see those individual aggregates in there.
So if we take and just run a finger through this soil, you can see that it's completely broken down. It's just mud.
Whereas over here, when you run that finger through this soil, those aggregates are still kind of held in place there. And again, like Joe said, thinking about how a soil that has more water-stable aggregates and that stability there, you're more likely to be able to hold your equipment up better on this soil versus getting stuck or having to wait extra days to get in the field in the spring to plant, or having to wait extra days to get in the field to harvest, because that soil is not going to be able to hold you up and to get in there.
Because this soil doesn't have any aggregate stability, anytime it gets wet, it breaks down. And that's how crusts are formed in fields. So once this mud dries, it will dry solid. And all of those sand, silt, and clay particles will dry together as one solid crust. Because of that, we'll have water infiltration problems, we'll have air exchange problems in that soil. The soil biology will not be able to function as well because it has less oxygen and less water available to it. And this soil, this unhealthy soil, will function a lot differently and a lot less than this healthy soil. In the springtime, if this crust forms over a new seedling or a new seed that we spent a lot of money to put in the ground, that crust will form and this will form as one solid chunk, and then that little seedling will have to try to push through that.
Whereas with this soil, our healthy soil in the no-till system, because we have all of these aggregates, water is able to infiltrate through this system, and we're also able to have a good gas exchange into this soil, making it an aerobic soil, a habitable place for our soil microorganisms. And it's essential that we have these microorganisms here because they are the ones that rebuild those biological glues on these aggregates. So this system continues to function and regenerate itself because we have that water infiltration, we have that air exchange, we have that nutrient cycling, and the soil microbes that live here play a key role in that, and they then continue to help rebuild these aggregates as they're functioning and living in this system. These trays of soil were actually cut out of a field. The edges on the bottom are sharpened, and so that we can actually pound them into a soil so that we can get an undisturbed soil profile. And on this side over here, again, is a system that was heavily tilled, worked in the fall, worked in the spring, and you can see not only the color difference, but what the surface of that soil looks like. We have that cracked soil surface, it's sealed up, all of these different things that we typically talked about earlier when we don't have a healthy soil or when we have a loss of function and the soil is collapsing on itself. And then this soil here, we have a well aggregated soil surface. We have some soil residues here, and this is in a no-till system with cover crops. So again, long-term no-till with a long-term use of cover crops every year after harvest. So we're going to rain on these two soils, and on the bottoms of these there's a metal tray that the soil is held on, and then we have below that a container, and in front of that another container, and those will be essential for when we start to look at that runoff or infiltration of that rainfall event. All right.
So we have a measured amount of water here, and this is calculated to be about an inch of rainfall on these soils. This top container has holes in it so that to let the water through. And you can see we have these soils pretty well level. Not perfect, but really representative of what we have across much of the state. So when we do this, we've talked a lot about soil function and how to look for some of that soil function, what our indicators are of soil health. So as we pour this water in and we watch what happens, think about what our indicators were of soil health and see if you can recognize some of those functions or lack of functions. So as that water runs onto that soil, immediately we have runoff on this unhealthy system. You saw that that soil had indications of a crust. You saw that that soil did not have any cover. You saw that it probably had too much residue breakdown. We poured that inch of water on there, and it was a pretty fast inch of water, admittedly, but we get hard driving rains, and that happens on our soils. So if you look, immediately we got runoff, and what was left, we've got ponding on that soil surface.
On this one over here, we did not get any runoff, as you can tell. That soil again we had a well aggregated soil surface. There was no crust on that soil. we had a decent amount of residue, although admittedly, I would like to see a little bit more evenly distributed residue and soil cover on this tray. But I've been using these for a few months now, so we're actually having some natural residue breakdown even on this tray here. So we didn't have any runoff, but what we had was infiltration. So all of that water that we poured into there actually infiltrated onto the soil, into and into that container below. If we could infiltrate 1 more inch of water over every acre of cropland in that watershed, how would that impact water quality and potential flooding downstream, and also just the function and health of the soil that you own and take care of, the land that you have, if we could get it in the soil versus running off and leaving that system.
Once again, we rained an inch of water on these soils and no runoff came from the healthy system. So that whole inch is yours to keep. We rained an inch of water on the unhealthy system and 3/4 of that ran off. And that's gone. And you will never get that back because it's in the Wabash and it's down to the Gulf of Mexico, along with your topsoil.
So we encourage you to take a walk through your farm and do this quick soil health assessment and get a better understanding of what does your soil look like. And then talk to your farmer about what practices they do to promote soil health on the farm. There are many resources to help with this conversation, and we're here to help along the way. There are also many funding opportunities available to help actually put practices like cover crops that will improve soil health and improve water quality on your farm. Because healthy soils stay on the farm, while unhealthy soils wash away to streams and creeks that drain to the Wabash River. That unhealthy soil is still holding nutrients like nitrogen and phosphorus that can cause harmful algal blooms in our waterway. The clay and the silt in that soil too breaks apart and stays suspended in the water column, just like we saw in those tubes. These are impairments to water quality. And so together, we can improve practices on our land so we have better water quality in our waterways. And so wherever you are along the Wabash River, feel free to reach out to our organization for resources about funding opportunities and programs to improve soil health in your farm and water quality in the watershed.